A blue screen feels like the end of the road. For a Tier 3 engineer, it's the beginning of the investigation. In this lesson, we treat a crash as data, we capture the right dump, load symbols, and run the WinDbg command that names the faulting module. Then we do the same for a frozen application that never crashes at all. Reframe the blue screen. A bug check is the kernel deliberately stopping, because continuing would corrupt the system. That stop produces a crash dump, a snapshot of memory you can read afterwards. A frozen app produces no dump on its own, but you can force one. Either way, a crash is not a mystery. It's evidence, sitting on disk, waiting for a debugger to read it. Before you analyze, you must capture. For kernel crashes, the kernel memory dump, or the modern automatic setting, is the right default. It holds enough kernel memory to name the faulting driver and read the stack, without the disk cost of a complete dump. Check the configured type with getItem property on the crash control key. Value 1 is complete, 2 is kernel, 7 is automatic. Kernel dumps land at memory.dmp. WinDbg maps raw memory addresses to function names using symbols. Without them, every frame is a hex address and your analysis is worthless. So before anything else, point WinDbg at the Microsoft public symbol server with .sympath, then .reload. If you ever see the message symbols could not be loaded, stop, fix the symbol path and reload before you interpret a single frame. The workhorse command is bang analyze-v, analyze, verbose. It decodes the bug check code, identifies the likely faulting module, and prints the stack at the point of failure. The bug check code classifies what rule was broken. For example, D1 means a driver touched pageable memory at too high an I or QL module name and image name point at the code that was executing when it faulted. That's your prime proximate suspect. Now stay disciplined. The faulting module is where the crash surfaced, not necessarily where the corruption began. A Microsoft driver can fault simply because it tripped over memory that a third-party driver corrupted upstream. So before you blame the named module, read the full stack with the k command, and list the loaded modules with lm to spot anything recently loaded or unsigned. The visible faulting frame might be the victim, not the culprit. A hang never bug checks, so there's no automatic dump. You capture the live process yourself. With procdump-ma or task managers, create dump file. Open that user mode dump and run ~k to walk every thread stack. You're looking for what each thread is waiting on, a lock, a slow remote call, or two threads deadlocked against each other. The wait, not the work, is the story in a hang. Finally, classify the root cause. If you see the same bug check code naming the same module across repeated crashes, that's a strong driver defect signal. Verify its version, signing, and known issues. If you see random bug check codes naming different modules each time, suspect corrupted state or failing hardware, like bad memory. Let the pattern across multiple crashes guide attribution. A single dump rarely settles it on its own. Recap. Capture the right dump type, then load symbols before you read anything. Run bang analyze-v, but read the full stack rather than blindly trusting the named module. For hangs, force a dump and inspect what each thread is waiting on. Your task: confirm and set the dump type via crash control, open a kernel dump in WinDbg, run analyze-v and record the bug check code, module, and top of stack. Then proc dump a hung process, run ~k, and conclude driver defect, corrupted state, or hardware. Next up, network diagnostics.